morning. I'm pleasantly surprised to see so many people here. I didn't think that we were going to have this many. If Oprah were here, she'd give you all a car just for showing up. I've ordered extra coffee for you. And around the room are monitors that you can follow all of the PowerPoint presentations on. Today we're going to start our session with emerging energy technologies. And to lead us in this discussion, we're pleased to have with us Dr. Nuala Cowan of the World Bank. Nuala?
Thank you, John. Welcome, everybody. And again, thank you for getting here on time. We know the weather hasn't been our friend, but we're extremely grateful. As John said, our panel this morning will be on emerging energy technologies, and I would like to welcome our panelists. We have General Rick Devereaux, Mr. Christofer Mowry, we have Mr. Frank Prautzsch, and Dr. Kevan Weaver. And we're going to start the panel this morning with a brief little presentation to set the scene from each of our contributors. Then we'll have some panel questions, and we'll take some questions from the floor. General Devereaux, he is currently the Executive Vice President for Government Affairs at Viviz Technologies and also the President of Devereaux Consulting, LLC. And before joining the private sector, General Devereaux served for over 34 years as an Air Force pilot, functional expert, and commander. He completed 2 tours on the Joint Staff of the Pentagon in operations and logistics, and his last job on active duty was the Air Force Director of Operational Planning, Policy, and Strategy at the Pentagon. In his current position at Viviz Technologies, he oversees relations with federal agencies regarding the development and regulation of long-distance and wireless electrical power. And General Devereaux has been a strong advocate for moving the military towards more resilient and sustainable energy solutions and transmission systems, and he volunteers for the Citizens Climate Lobby, where he focuses on the national security aspects of climate change and fossil fuel dependence. And the floor is yours again.
Thank you, Nuala. Yeah, hello everybody, good morning. I apologize for my voice. I think the weather is playing havoc with it, but we'll try to get through this. You know, yesterday, Gary Dirks mentioned a quote that I really liked. He said, "What is missing is the imagination." Well, I'm going to talk about one emerging technology that is packed with imagination that would really, if it's able to scale, change the energy landscape of the world. As they're pulling those slides up, you know, I have a background, as Nuala said, in the military. And during my time in the Air Force, one of the things that we, yeah, if we could back those up to the first. Okay. One of the limitations for military operations is energy. You know, in the U.S., it's sort of our greatest strength in terms of the energy that enables military operations, but it's also a point of vulnerability when you consider the long logistics lines, the fuel requirements for generators and so forth. So I want to talk today about what if we could cut the cord? What if we could move to a world where transmission of electricity was wireless, and therefore it was less relevant about this distance that we talked about yesterday between the sources of energy, often mismatched to the demand for energy. So I want to talk to you a little bit about the world of wireless power. You know, we know that our current transmission grid is vulnerable. It's limited. Somebody once remarked that if Thomas Edison came back, he'd take a look at our grid, at our generation, and he'd see a lot that's familiar. Alexander Graham Bell, if he looked at the way we do telecommunications and information technology, he'd say, I recognize none of this. But when it comes to electrical power, much of our technology is still 100 years old plus, and it's vulnerable to weather effects, it's vulnerable to physical attacks, cyber attack, and we're limited in terms of where we can place renewable sources of power because they need to be relatively close to that demand for power. And even yesterday we heard things like high voltage DC transmission, which can help bridge that gap, but there's a lot of regulatory hurdles and other limitations, cost, environmental impacts in putting in those long-distance DC lines. So what our company, Viviz Technologies, is envisioning is a world of wireless power transmission. You know, the way we do electricity today, of course, we have our generation source, we have a substation that ramps up the voltage, high voltage transmission lines to another substation, and then to the ultimate customer, the users. Well, what if we replace that transmission segment with a transmission tower that could beam the power wirelessly from any generation source to any downstream substation, and then from there throughout a local distribution grid. So our technology is really focused on that transmission segment. We'd still rely on a wired grid for the distribution, but for the long distance, long haul transmission, that would be wireless. So how does this work? We're working with a technology called the Xenic surface wave. This is an electromagnetic wave that actually, instead of transmitting line of sight, it actually follows the curvature of the Earth. Kind of like a glove that wraps around the planet. At low frequencies, it has the advantage of being very long range and very high efficiency, as our testing has sort of demonstrated. And the beauty of this wireless transmission system is it's like a wireless extension cord. In other words, there's no energy loss until there's a connection established to a downstream load at a substation or, again, at that local distribution grid. It doesn't get old, it doesn't age out like our current transmission grid. It's impervious to weather, and even EMP effects are basically limited in terms of an EMP attack or some kind of a solar flare. So I'm sure some of you are saying this sounds like science fiction. If this is real, why hasn't it been discovered earlier? Well, if there's any engineers in the crowd, you've probably heard of a guy named James Clerk Maxwell, who's the father of electromagnetic theory, and then a guy named Heinrich Hertz, who is sort of the father of what we consider radio. Hertz wrote all the theory and the discoveries related to radio transmission, and everything from Wi-Fi to broadcast television is governed by Hertzian radiation, if you will. But back around the turn of the last century, there were a couple German physicists, a guy named Sommerfeld and Xenic, who worked on this phenomenon called a surface wave. And in fact, there was some debate about whether Marconi's signal that went around across the Atlantic was a surface wave or a Hertzian wave, because they couldn't figure out how could a wave that's traveling line of sight wrap around the curvature of the Earth. There was some testing that was done in the 1930s, and basically the Xenic surface wave was dismissed due to the inability to launch it and measure it and successfully explain it in the mathematics, and it kind of caused what I call a scientific head fake to the community. But subsequently, our scientists at our company did a lot of research and experiments, and they were able to successfully launch this Xenic surface wave at high frequencies successfully. So now we're working on what we call a global demonstration project. We built a 200-foot high tower out of fiberglass. I've got a quick little video showing it. It's got a aluminum capacitance dome on the top. That charge terminal at the top will reach a level of 200 million volts, and we'll launch that first global Xenic surface wave at very low frequency, down around 18 kilohertz. And for you geographers in the crowd, we'll be placing sensors on great circle routes extending out from our transmitter location, which is just south of the Dallas-Fort Worth area, in a little place called Milford, Texas. This is not long-term project. Testing is actually going to start within the next 30 days for the signal, and then sometime within the next year is when we expect to do our first power delivery overseas. I've got a little video that'll just give you an idea of the scale of the tower here.
There's not another tower in the world as tall as this one that is made entirely of non-metallic materials.
We designed this from the beginning to be a commercial structure, not just a test laboratory for proving that we can send a xenic surface wave globally.
The most unknown was the adhesive that we had to use for all of the structural connections, not only on the bolts but also on the plates that made the connections. We were able to manage that by building an environmental control space.
The superstructure is made of fiber-reinforced polymer. We stretched the limits of the available technology of that material.
We had to come up with a new manufacturing method to make fiberglass columns and beams that were long enough, strong enough to support a structure of this height.
So we had to do a lot of empirical testing on the materials to ensure that they would perform as specified.
And to be able to support the charge terminal on the top.
Charge terminal is made of aluminum plate, 30 feet in diameter. It's, as you can see, it's a hemisphere with a torus on the bottom. The weight of it is approximately 30,000 pounds as it was lifted into place. That includes all the rigging, and it is hollow inside with equipment designed to service the tower for its life. We had to learn new techniques for fabrication of the FRP materials, how to fabricate it on site, how to join it. None of that was documented in any other handbook or manual that exists currently. All this is unique to this project.
Well, we spent a fair bit of time documenting and putting together an instruction book to be able to transfer that knowledge that we've gained from this first project onto future crews. So I feel fairly comfortable being able to repeat that.
And then when we're ready to start our first commercial structure, we can basically have all of the materials procured and constructed and turn a new one on commercially within 12 months.
But the point of this technology is it's sort of transformational in nature, as you can imagine. If you can get power from a solar field in the sub-Saharan African desert anywhere on the globe at what we believe will be about 85% efficiency, think about how that changes energy. Think about a world where the need for pipelines, for tankers, for moving energy molecules around goes away. Why not just, at your source of energy, electrify that energy, generate it, and move that power wherever you need it, anywhere on the planet? So truly a transformational technology. And as we talked yesterday about different technological innovations and advancements, most of what we talked about was iterative change to the technologies that are already present. And I think to get to Paris and to get to some other sort of goals for our planet, we got to be thinking about new technologies that'll be disruptive and totally change the energy scene. Just as the internet, didn't produce any more information in the world, but what it allowed was universal access to the highest levels of information. This technology, if we're able to scale it, will allow a high level of access to energy and clean energy anywhere on the planet. Thank you very much.
Thank you very much, General Devereaux. Next to take the floor is Mr. Chris Mowry. Chris joined General Fusion as its CEO in 2017. He's got more than 30 years of experience in global energy and infrastructure sectors, and he has led an exceptional portfolio of projects, including those in power, oil, gas, and energy management, and the automation and process industries. And prior to joining General Fusion, Mr. Mowry was the founder and CEO of the industry leading to small molecular reactor company, Generation M Power, also following roles with B&W Nuclear Energy for the Babcock and Wilcox Company, WSI, and GE Energy. And throughout his career, Chris's focus has remained on the commercialization and innovation of clean energy technologies.
Thank you. Good morning. So, start with maybe this most infamous slide of the 21st century for those people involved in energy. And it's a graph of the trajectory of carbon emissions in the planet from the beginning of the century and projected out over the next 50 years. And this is obviously what's motivated a lot of discussion around the world. It's what's caused the Paris Agreement to come into force, and it's something that anybody who spends any time on energy really thinks about quite a bit. And just to kind of put this in context, I think for those of us in the room today, we probably consumed on the order of $10,000 worth of electricity since we got up this morning, and that's for 100 people. And that is part of what's driving this curve and making this curve go up. And you look around this room, there's six large LCD screens here, eating up a lot of power. And so the demand for power, even in developed countries, is just going up and up. But as we all know, there's been a lot of effort put into trying to decarbonize the energy industry. And this is a pretty telling statistic here. After 20 years, we're almost 20 years into the 21st century, and you look at what the carbon footprint is and the mix of energy today, and in spite of a lot of efforts, it really hasn't changed much since the 19th century or the 20th century. And if you project this out, this is the best guess at what the energy mix is going to look like 25 years from now. It's not changing. It's not changing much at all. Renewables, solar and wind, they're going to double, but they're going to double from 1% and 2% to 2 and 4%. So maybe going from 3% to 6% of the total energy produced on the planet. This is why that carbon curve is not turning. So look at this thing a little bit deeper and ask yourself, how can this be? How can we not be turning this thing? And I think a great case study is Germany. Germany is probably the poster child for countries that have made a concerted national effort to invest in energy transition. They have this thing called Energiewende, and they probably spent, since the beginning of the century, $100 billion trying to decarbonize their energy industry. And you look, this is a statistic, a snapshot of energy generated and consumed across Germany, probably within the last month at one particular point in time. It's not very good. Almost 500 grams of CO2 per kilowatt hour of electricity that's produced. That's actually more than it was at the beginning of the century. And you look at the energy mix down below, it's dominated by coal and gas. And there's some wind there, and there's hardly any solar. And the amount of contribution from wind and solar is only about 20% of the total amount of wind and solar power that's been installed for that $100 billion. So in fact, Germany is an example of how, because of a lot of factors, a huge investment in energy has not really changed the carbon footprint of the country. So if you look around the world and say, well, what's going on here? Here's two examples. One is a country that is a developing country that's just getting started on an effort to decarbonize. And you can see this is probably on the far end of the spectrum of carbon emissions. And they're a country with almost 100% coal and gas as a source of power. What are their options? What are their options for decarbonization? It's a country that's on the equator. So on the equator, there's no trade winds. And surprisingly, there's very few clear days in Malaysia. And so Wind and solar, while they may help a little bit, are not really very good options for Malaysia. Now, let's go somewhere else. Let's go to Norway. Norway is blessed with mountains. Norway doesn't have a lot of people. And because of these two geographic factors, Norway has a carbon footprint almost zero, 29 grams per kilowatt hour of CO2. They are able to basically derive all the electricity on their grid from hydropower. Unfortunately, Norway and the geography of Norway doesn't apply to most of the world. So what are we going to do to turn this carbon emission curve in the 21st century? Enter fusion. So fusion is the power of the stars. Fusion is the most powerful form of energy in the universe. It's the densest form of energy. And when you think about what's happening to world populations throughout the 21st century, Tokyo is going to have 75 million people in it by the end of the century, for example. You need a very dense form of energy in order to provide power for Tokyo. It's also low impact, basically no emissions, no long-term waste. It's on demand. That's what we mean by dispatchable. And very importantly, it's manufacturable. What do I mean by manufacturable? The power of fusion, the fuel of fusion comes from water. 1 liter of fusion fuel is enough fuel to power 10,000 homes for a year. And anywhere there's people, there's a liter of water to be used as fuel. So really, it is, in some sense, the only form of energy that is manufacturable without reliance on some type of supply chain, whether that's an oil pipeline, a gas well, wind, sunshine. You can make fusion with a liter of fuel. Something else that's really important when you think about bending the curve and changing the energy mix is economics. While some countries, North American countries, for example, can afford to spend a lot of money on energy technologies that are not cost competitive with existing fossil fuels, the reality is that in the developing world, if you're going to bend the curve, you have to have a competitive solution. And luckily, fusion is the lowest cost form of electricity that there is. And the world's taking notice. The energy industry is taking notice. Since the beginning of the century, there's been more than 24 private fusion ventures started. More than $1 billion of venture capital has gone into commercializing a practical solution to fusion. There's a lot of reasons for this, but I think the great reference point for us is SpaceX. This is the SpaceX moment for fusion, where we're trying to take a technology that's been developed in laboratories and research facilities around the world and make it something that's practical and usable and something that can be deployed around the world to help bend the carbon curve. Thank you.
So next up, we have Mr. Frank Prautzsch. Frank is the president of Velocity Technology Partners. In his current role, he works with and for the government as a senior consultant to the National Capital Region Remote Sensing Center on disruptive and emerging energy sensors, communications, space, navigation, and material sciences. And after his graduation from the United States Military Academy, he served for 22 years in the military in a variety of capacities. And in his post-military career, he's focused on advancing military space and machine-to-machine IoT environments and taking on personal passions in renewable energy and climate change research.
Thank you, Nuala. It's always a pleasure to be here at AGS. Thank you for having given me the opportunity to graduate from lightning rounds last year on flying cars and jetpacks into something that is perhaps more endearing, and I hope you will remember this day the rest of your life. All right? Because the biggest person in the room is going to talk about nano energy. All right? And hopefully you'll also get a take on this from a perspective of that this is, I live in a world of looking for disruption. So take it for what it's worth. I find this a candidate for disruption. in its biggest ways. So I will introduce you to the nanobox and the process of thermionics and take it from there. So in looking at nano energy and the nanobox, which I have in front of me here, this is the little guy that you see there at the 5 nanometer level. The deposition of molecules on this device are roughly 1/15,000th the width of a human hair through a proprietary process that allows us to be able to do this. The advantage to it is that this is not a battery. It is an energy harvesting device that operates between thermal separations. So why is this important? It's important because the technology has been around since 1853, but the manufacturing techniques in order to make it practical have been around for about a year. So what makes this successful is the ability to do disruptive electrospray manufacturing. I call it 4D printing, not 3D. So we do X, Y, Z, and changes in metallurgical techniques and composition of the materials that go through a high pressure nozzle at extreme voltages with the deposition of particles at 5 nanometers. Specifically, every cell knows exactly where it's going to go after it's shot out of a needle. So what is thermionics in general? I have an anode and a cathode, no different than anything else. In fact, thermionics, Thomas Edison experienced thermionics all the time with vacuum tubes. It was the arcing of vacuum tubes after they were off. He didn't understand what that was all about, but it was thermionics. The metals wanted to continue to transfer electrons between a metal that wants to shed electrons and one that wants to collect them. What we have done is we've refined the process for being able to keep a space between the anode and cathode using a nanofluid and some graphene technologies that allow us to harvest the electrons and make it an effective cycle. So when a load is applied to this, it continues to operate. And the significance of that is that it scales. So what? The so what to this happens to be that we're reaching a stage now where something the size of a postage stamp can run a remote sensor. Something the size of 6 or 8 of these postage stamps can run a cell phone. Something the size of 800 or 900 of them can do a kilowatt of energy and perhaps perform a function in space without solar panels or a battery. And a cubic meter of these will run a neighborhood or an off-grid industrial complex or a high-rise or Columbia University's campus. And for me, that's game-changing. It also will change geography, and we'll talk about that in a moment. The additional so what? Everybody kind of goes, oh, this is voodoo, Frank. I have no idea what you're talking about. Don't believe you. Come on, you're violating all the laws of thermodynamics. No, I'm not. So the truth of the matter is, independent testing was done at Waseda University in Japan. We looked at a variety of gradients to this, and this little guy performed for 3.7 years. So it continues to keep on giving when there's a load applied. Now, if you don't think that's game-changing, I'm going to basically tell you that the lithium-ion world will be in for a culture shock. And number two, so will all of the recharging people that have cords and cord systems and DC rechargers. How many of you have a recharger in your pocket just in case your battery runs down on your cell phone? Actually, the energy source will outlast your phone. In fact, your phone will be obsolete before the cells are obsolete. The performance curve you see up there is pretty statistical of what happens. There's an initial start phase, and then it continues to work over time. Mathematically and hypothetically, it'll last 11 years before the shedding process deteriorates to a point of failure. Everybody needs a comparison, so let's bolt this against the lithium-ion concept. It has 40% greater energy mass density. It is 10% of the weight. It is mass producible. That is an error there. It's not $40 per kilowatt hour. It's $40 per kilowatt hour amortized over 11 years, which equals 0.0004 cents per kilowatt hour up front. So conceptually, it's not free energy, but it's getting there. Major feature, no recharge. We did a small market survey to find out that people will spend up to 5 times more for a phone that does not have to be recharged. That's the irritation. There's no risk for explosion. It is not an electrochemical event. It's a thermal event. It's fabless lights out operation. The printing technique that I showed you could be set up on a conference room table and you can make your own. Not that the equipment is probably make your own, but it's something to think about. And there's no hazardous waste, and it's totally recyclable. So applications, pick your swim lane. We can start with everything from gadgets and gizmos and embeds and medical devices and in the milliwatt range. We can look at wattage systems that include UAVs and Roombas and laptops and cell phones. We can move forward into the kilowatt range where a standard household does about 5 kilowatts or less. So you can have your own off-grid or your own resilient network at your home. So introduce cyber attack and start laughing. Or you can bump this up to megawatts and power communities, do advanced locomotion, fly cars, advanced electric propulsion for aircraft, et cetera, et cetera. So not saying it's a cure for everything, but it's going to change the way we consume electricity because we are not relied upon a battery. What's a geographical impact? There's immediate and continued sustainment of carbon reductions. And for all these fun people that have EVs, I'll be upfront with you, they are not. They have a terrible green footprint because all of the problem has just been moved to a power plant, not to your car. So in this case, the vehicle is in fact truly green. Electric vehicles, reduction in weight, significant reduction in dependence on oil, gas, and other sources. It's safe, efficient, resilient, and in my opinion, it will equate similarly to the cell phone moving into the developing world, where one would question, why would you want to put in a landline? If we have this form of technology, why would you ever want to have a power grid? There's a large assemblage of documentation that relates to the intellectual property of this. The company in question that does this is Birmingham Technology. I'm not here to speak for them. I'm here to tell you that they exist and that the patents are very deep and international with a focus on made in the USA and USA only to start with. Oh, by the way, there's a $450 million thermionic plant being built in India, but it does not use this form of technology. It is basically rubber or basically metal stamping in sandwich form to do the same thing. Just in much greater inefficiencies, but for those that think that thermionics is not going to happen, it's going to happen. And my conclusion is we're going to see some freedom from recharging in probably 3 to 5 years. We're going to see wider adoption of that thermionics because it is a major carbon sink. And we're going to see applications across the board that affect us in our daily life as a consumer and as an energy force of the future. So that's my thoughts, and hope you understand where we're going. Thank you.
Thank you very much, Frank. And To our final speaker this morning, we have Dr. Kevan Weaver. Dr. Weaver has spent much of his career in advanced reactor design and analysis. He recently rejoined Idaho National Laboratory in the spring of this year and is currently the technical lead for reactor systems and safety, where he leads an effort on advanced reactor fuel testing and safety. Prior to that, he worked at TerraPower from 2007 until this year, where he was responsible for identifying, developing, and maintaining US and international joint programs and relationships for technology development. Before that, he spent several years with Idaho National Labs as well. His experience has allowed him to focus on some of the critical technical challenges facing advanced reactor concepts, such as the development and testing of advanced nuclear fuels and materials. Dr. Weaver.
Great, thanks, Nuala. So I'm going to take a kind of the same tact that the other speakers have taken, but I'm going to go up one level perhaps on this, probably talking more on the level of, instead of getting into some of the specific technologies, talking about what the challenge is, because I kind of want to set the stage for why we want to consider what I'm going to propose. And I want to start out immediately by saying what I'm proposing is that we don't go all nuclear fission, by the way. And some of you, that may surprise you. You know, I'm here to promote nuclear fission power, but let me put it this way, when we talk about, or when I talk about the challenges that are ahead of us and that are facing us, it's going to need to be all hands on deck. We're going to need everything that we can get. Fusion, fission, transmission, because transmission, by the way, is a huge piece of what the problem is right now and one of the challenges that we have. Batteries, whether it's thermionic or whatever, I think we need everything. Chris actually put up a graph that showed some of the problems or challenges that we're going to run into. So this particular slide here focuses specifically on the electricity side. So if you look at energy, you can basically divide it into a three-piece pie, right? So you have a third and a third and a third, roughly speaking. A third of our energy goes into producing electricity, a third of it goes towards transportation, and the other third goes towards industrial processes. So if you think of industry, you're thinking, you know, things like steel mills, and other places like that where they make stuff, you know. And so if you look at the whole energy circle, you got a third and a third and a third. I'm focusing on electricity because it's one of the fastest growing of those thirds. And in fact, not only fastest, it's actually starting to incur and get into some of the other third areas, right? Like transportation, which I'll talk about also. And so if by 2040, if we go from the more than 7 billion people we have on the planet now, and we go to more than 9 billion people, and you look at I saw this on a slide, the haves and the have-nots, and you want them to also come up to the same standard of living, we're going to need a lot more energy than we have. And so for the 9 billion people, the electricity demand, and this is an IEA number, we should expect it to double. So we're going to need basically twice the amount of electricity that we have now. And that doesn't include some of the other things I just said, which is what if we start to electrify our transportation grid? This is a big deal. So a lot of you have seen this picture before. This is a NASA composite, satellite composite of the Earth, and you can see all the lights. But I think the thing that's interesting about this is and I'm not going to exactly overlay it because I'm not that good at doing the graphics myself, but if you compare that between the two, where you saw most of those lights are in those red areas, with the exception of maybe Greenland. But if you really look close at Greenland, the places where the people actually are, they're light, I promise. But if you look at that, this is basically world by income, which means standard of living in my mind, right? And I forgot what it's called. I already blanked on this. But if you go back to the UN and you look at what it takes energy-wise to bring people up from essentially poverty level into a level where they can live a good life. And when I mean good life, what I'm really talking about is if you have access to energy, typically you have access to medicines, hospitals, schools, all those things that go along with that. And if you get there, those that are in red are either there or all the way there, and then you can see the rest that are up and coming. And one of the things I want to point out too is if you look where the world population is, the majority of the population actually doesn't reside in those red areas. The majority of the population resides in the Southeast Asia, specifically China, India, and then don't forget about the billion and growing in Africa. So there's a mismatch here between the haves and the have-nots. And the nice thing about the standard of living and the energy correlation is that if you at least the idea is from a philosophical standpoint, if you can bring up the standard of living, some of the problems that we have can be solved. But one of the things we have to be careful of, and this was brought up in some of the other speakers' notes and their presentations, was if we have to have all hands on deck, then what is it that we're going to use to produce this power, this energy that we need? You know, that's a big question, and I think it's a question that we really need to sit down and ask ourselves. And part of the issue here is that this is not just a technical, and I love the technical. I mean, I love to stand up and I like to point out, okay, look, you know, if you get down into the materials and you look at the grain structure and all the stuff that goes on, that's sort of the fun professorial stuff, and actually I really like doing that. But when you go up to the next level, it's really socioeconomic and political that really plays even a bigger role in all of this. And so at some point, we're going to have to make a hard decision. And I think as humans, we typically run on crisis mode, right? In other words, we don't do anything until there's an absolute crisis. And I think what we're going to run into is we're playing this big experiment with our planet. And that big experiment, what's going to happen? What are we going to do? What's going to happen to the planet as we move towards more and more energy use of more and more resources? How do we get there, and how do we fix this? And I think the answer is not easy, number one, but the answer is that someone has to have a sense of urgency, or a group of people, or a country, or a world, a sense of urgency to get there. And I think there is a sense of urgency, but how do we get everyone to think together? Now that's a much larger philosophical debate, discussion, et cetera. But what I'm proposing here is that we actually have the resources between fusion, fission, wind, solar. If you want to go non-carbon, in fact, you could even take the fossil, and if you do sequestration, all of it, so that we're not playing this big experiment on the Earth, and then everyone can get the energy they need. So if we remain on this current trajectory, how can we have all this energy and not deplete the resources, et cetera? So now I'm going to get to my specialty and why I'm here, even though I essentially said, look, we need everything that we've talked about, including what I want to talk about here. So on nuclear, if you look back, nuclear, at least as far as looking at fission, you know, this was discovered back in the 1930s, 2030s, up to the 40s until we actually produced a weapon using nuclear. But there's also the other side of that, which is it produces power. And like fusion, it's not as high an energy density as fusion, but it's pretty darn close, which means you can have a lot of energy compact in a really small area. So you can have it closer to the areas where you need it. Of course, if you can get to these transmission capabilities, then it means you can site it anywhere and then move it from there. But the reason I say nuclear is because we have to have it all. If we're going to make the difference that we need to, we're going to need it all. And so I'm going to spend the next 2 minutes, I think, to talk really quickly. So what are the emerging technologies for nuclear? In the United States, there are between 40 and 50 startup companies. I actually worked for one of them, TerraPower, that was looking at this particular technology, but more importantly, the subset of technologies within nuclear. And when you talk about nuclear, you can talk about what cools the reactor. That makes a difference. It makes a difference in temperature. That makes a difference in thermal efficiencies. The size of the reactor, that can make a difference both in siting, portability, et cetera. And beyond electricity. And so what I'm saying is that all these energy sources, including nuclear, can move beyond just the electricity piece too. They can move into the process heat side because that hits the industrial side. Right now what we do is we burn something, typically coal or natural gas, to get the heat that we need for those processes. What I'm saying is that all of these energy technologies we're talking about can get you there without having to burn the fossil. And in fact, I'm going to add a little side note in here. It turns out coal, which tends to be the bad guy in most discussions now, especially when you talk about climate and energy, the fact is that there is a role for coal, and that role for coal is in some of the materials that we're talking about, right? You can change that coal into the nanotubes and the other things that you need. Rather than burning it, you can turn it into products that are worth a lot more. But the thing is to get to all these products, you have to have energy to get there. And so and I've said this, I think, 4 times now, we have to have it all. We have to have it all. We can't leave anything off the table in this case if we're going to make that difference. And in this case here, and I would be happy to answer questions about what kind of nuclear technologies, both small, large, et cetera, that will help in solving our problems. Thank you.
some questions for everybody on the panel. I'm going to ask you maybe to keep your answers to about 1 or 2 minutes so that we can get across the board, and then hopefully have some time from the floor as well. And I'd like to start with Rick, if that's okay. I'd like to ask you a little bit about the implications of emerging technologies around the cost and sustainability of energy sources.
Yeah, I think all of the technologies we discussed here have sort of benefits on both the cost side in terms of leveling the playing field for renewables or for sources of energy that have a lower carbon footprint. And it's really, I think that's where the market is going. Where can we get these triple plays? Where can we have our cake and eat it too? You know, the technology I talked about, it's transmission. You know, it's sort of agnostic in terms of the source of energy, but if you think about that, you know, if transmission, if we take that piece of the equation out as a limiting factor, then it really can enable some of the technologies in terms of generation that we've discussed. So I think looking for those synergies and ensuring that the policies and sort of some of the political discussions move in that direction rather than just looking at the shiny object is really the way to go. So looking for those synergies is really going to be where the big payoffs are with technology.
Thank you for that. Chris, if I could ask you, you spoke to the geographical constraints on energy technology, and I'd like you to elaborate a little bit more on that for the audience.
So, as I was mentioning earlier, we spent 20 years trying to bend the curve on carbon, and we're not really doing that, right? And I picked on Germany a little bit, so I guess I'll pick on them a little bit more, right? So in Germany, you have this scenario where the focus of new technology deployment has been really wind, primarily. Some solar, but wind. And where is it windy in Germany? It's windy off on the Baltic and the North Sea. Where is energy consumed? Energy is consumed in the south in the industrial areas. So you have this geographical disconnect between the supply chain for the technology that was chosen and where it's consumed. And you throw into that mix a reluctance to site new transmission lines through populated areas, and the fact that Germany happens to be surrounded by countries like Poland with a lot of cheap brown coal. And what happens when you have a lot of electricity demand in the south where it's not windy? Germany imports, you know, very carbon-intensive brown coal from its neighbors. So geography matters. I think one of the things that we've really learned in the last 20 years is that you have to consider the geographical constraints when you think about how to decarbonize a country's energy cycle. And the only other thing that I would add to that is that if you look at Germany from a policy perspective, one of the things that we've learned as well is that the policy was translated into a selection of a technology without thinking about the geographical constraint. And so industry optimized around the technology that was chosen by government as opposed to the higher level policy, which was, hey, decarbonize. Because if they would have left it there and had just imposed let's say a carbon tax, you would not see the energy mix in Germany that you see today, and you would actually see, for $100 billion, you'd see a huge reduction in their carbon footprint. And instead, they're on a road to nowhere.
Not very optimistic, no?
There's a lesson to be learned there. There's a lesson to learn, right? And that is that government should set the policy, but not dictate the specific technology solution, because then industry optimizes around the technology that government selected rather than the policy goal. If you spent $100 billion trying to achieve a policy goal of decarbonizing the German industry, much different answer. And I think Germany and I think the world is learning from those lessons, and I think in the future you're going to see a much different approach by governments as they try to actually bend the curve.
Support innovation rather than direct it. Thank you very much for that one. I've got a question for Frank. With the efficiencies and safety of wireless power, how do you think we're going to implement the replacement of the aging grid with wireless powers and other solutions?
Well, I think it's important to look at, again, we're not going to be able to snap our fingers and have this happen overnight. What we need to do is experiment, learn, prototype, look at efficiencies. When I look at the existing power grid, where efficiencies for an end consumer with a load will rival probably 56%, maybe less. I mean, basically, the pathetic thought is that 57% of the energy we produce on the planet is wasted. So we have to do a full court press in looking at every place where we can make a difference in changing those outcomes. And some of those are definitely in the wireless area. When I see efficiencies of 85 and higher percent as opposed to existing KVA lines that aren't, then one would wonder what perspective are we actually after. An additional side note, and this is actually a side benefit out of Rick's discussion, is the fact that at very low frequencies we actually have the ability to block radiation. It's a known fact from NASA. So actually, this is strange but true. Wireless energy transmission actually becomes a mechanism for decarbonizing the atmosphere. And so aside from it being less lethal than any of the power flux densities that we have on the grid right now, it is actually in practicum a smart thing to do by consequence for environmental change and protecting our planet with an outer shell to preclude Van Allen radiation and to an extent carbon dioxide.
Thank you, Frank, for that.
Yeah.
Kevan, I have a question for you.
Sure.
You mentioned the transportation sector in your talk. And as it continues to move towards electricity as its energy source, how does that impact electrical generators, including current transmission capabilities and other infrastructures?
So the first thing I want to do in answering the question is, I'm sure everyone knows, and if they don't, now the biggest emitter we have, one of the biggest emitters we have in the United States is the transportation sector. It just it jumped up. And so there's got to be a way, and whether it's electric cars or some other way, to make it so that it's not so carbon intensive. And one of the ways to do that is through electricity. And you can see that if we do from electricity, you have these companies that have come in, including the what I'd call the old standbys that are now looking at electrification. But for example, if you go to Europe or to Japan, all their trains are electric, correct? So as we move towards that, then those three pieces of the pie, now all of a sudden you've incurred into 2/3 of that pie, and that another third of electricity. That's the doubling, right? But that's the doubling even without the population growth. And so now you have to worry about transmission for sure. You have to worry about the infrastructure. If it's going to be lithium-ion batteries, you have to worry about where you're going to charge these up, who's going to provide that infrastructure, those kinds of things. So projecting out into the future, and I'm looking at it from the energy supplier standpoint only, and partly the transmission, it's going to be a big challenge. And there's a lot of work that's going to have to be done if we're going to get there.
Okay, thank you for that. Mm-hmm. I believe we have about 3 or 4 minutes left. So do we have anybody on the floor that has a question for our panel? Please, if you can keep the question brief. Thank you.
Good morning, and thanks for your contributions. My name is Antje Danielson. I'm at the MIT Energy Initiative, and I have 2 questions, but the first one is maybe a little more important. It's with regard to fusion. What are the remaining challenges, and how do the time frames for solving those challenges align with the time frame of the climate change challenge that we have? The other question, just in case we have time, is what kind of research is being done parallel to the technological research that looks at anticipating potential environmental and ecological impacts from those disruptive technologies, either one. Thanks.
So maybe the first question, Chris?
So I mentioned SpaceX in my remarks as a analogy for what's going on in fusion. And I think that analogy is much more than skin deep. If you look at SpaceX or some of these other private access to space ventures, Elon Musk did not invent rocket science. He took, or oversimplify this, 50 years of Apollo and NASA research into rocketry and sprinkled some private innovation and modern 21st century enabling technologies on top of that fundamental knowledge of rocket science. Things like 3D printing, high-speed digital control systems, big data. And with that, he didn't invent rocket science. What he did is he made rocketry and access to space practical, better, faster, cheaper. That's exactly what's happening today in fusion. After 50 years of research into fusion, you see this proliferation of private fusion ventures. They're not trying to prove that fusion works anymore. Fusion works. What we're all trying to do is make a practical and cost-effective version of fusion. And we're using the same exact enabling technologies that weren't available 20 years ago to make this thing happen. We use in particular 3D printing. Commonwealth Fusion Systems, which is just recently spun out of MIT, is trying to use modern high-temperature superconducting materials that didn't exist 20 years ago. So what's happening today is that new doors are opening to accelerate the completion of a commercialization of this technology, because you have this coming together of the development of science with other enabling technologies today. And so what's exciting is that these efforts, because they're commercial, they're backed by private investors, are happening on a time scale that's relevant for climate change. These are not 50-year programs. You're not going to find any investor willing to put money into a program that has a 50-year time horizon. These are 5- and 10-year horizons, and those time horizons are relevant for climate change.
Thank you very much. Anybody else in the panel want to add to that? No? You're good? Do we have any other questions? Maybe another one from the floor?
Hi, my name is Daniel Whalen. I'm a teaching fellow from Parkdale High School in Prince George's County. My question is specifically for the nanotechnology and the wireless transmission. I was meditating from yesterday and thinking that the places where the need would probably be the greatest for that would be in developing economies. And it might take, because of the presence of our traditional technologies in our current economies, more time for it to pick up here. So are the technologies that you're developing, will they be easily scalable for developing economies quickly?
Yeah, of course, they will scale to meet developing economy needs, and you saw a graphic of Africa, which is blue and everything else is red. Having said that, it's also not just nation states, it's emerging platforms and systems that are technologically based that are on the horizon. So I will debate twice whether a regional jump jet has to have Jet A or operate on electric propulsion. I will reason whether or not I can't upgrade a Tesla so that it doesn't need a lithium-ion battery. I will reason as to whether your house has to run on Pepco. All right. So it's important to fathom through not just where there is a demand, it's also to fathom through where emerging technologies are going to take place. Let me also add that, again, we're dealing with technologies that have existed for decades. So it's not an issue of haves and have-nots. It's not an issue of, and I segregate invention from innovation. We love to say that we're innovators, but we're trying to make stuff. For me, that is not innovation. Innovation is applying what we've made to do something for mankind that is different. And that is the secret sauce to innovation, as far as I'm concerned. So I think that's where we need to look downrange. Clearly, I think that as these new energy sources emerge, it'll be quite similar to a cell phone versus a landline. Why do I need one? All right? And so if I've got wireless power and I've got different kinds of energy sources that eclipse the need for landlines, then why do I have to have them?
I think that's all we have time for. Thank you for your answer. I'd like to thank everybody for appearing on the panel today, and thank you all for attending.